Number 10, number 17. Of course, your numbers might be a little different, but the problem is the same. Okay. So we have a 2x2 matrix, right? A. So A is 2x2. So I'm going to write 2x2 matrix like as so. A, B, C, D, okay? We don't know what the we don't know what the units are. We don't know what the entries are. What we do know is that the trace of A is 14 and the determinant of A is 45. Okay, we do know that. First of all, what's the trace? The trace is the sum of the diagonal entries, right? So this is A plus D. And then what's the determinant? For a 2x2 matrix is AD minus BC. So far, this is what we know, right? This is what we know. Okay, and what we want to figure out is are the eigenvalues. So what's the only way to find the eigenvalues of A? To find the eigenvalues of a matrix, you have to find a characteristic polynomial. So I want to find my characteristic polynomial. And we do so by doing what? Taking the determinant of A minus lambda I, equaling it to 0. So if I were to do that, this would be the determinant of what? Of A minus lambda, D minus lambda, B, C, equal to 0. Right? And to find the determinant of a 2x2 matrix, again, it's the same idea, right? So we got A minus lambda, D minus lambda, minus BC, right? Equals 0. We do a bit more of distribution and we get AD minus A lambda minus D lambda plus lambda squared minus BC equals 0. See a lot of letters, but remember, this is a polynomial. So I put a lambda squared first, then I do A minus lambda, D minus lambda, plus AD minus BC. Do you see what happens here? Do you see that I can factor out a minus lambda here? So this becomes minus A plus D lambda plus AD minus BC equals 0. But wait a minute. What is this? It's the determinant. And what is this? The trace. Very convenient, very nice, because then the characteristic polynomial is simply minus the trace, which is 14, lambda plus 45 equals 0. Wow. So we get a quadratic polynomial as my characteristic polynomial. And then solving for this, we factor, don't we? This becomes lambda minus 9, lambda minus 5. And then I get lambda equal 5, lambda equals 9. So the information we had in the beginning actually was very useful. the trace and the determinant of a 2 by 2 matrix appears every time in the characteristic polynomial. That's like the little insight for this problem. So whenever we talk about 2 by 2 matrices, the determinant of that 2 by 2 matrix is the constant term of my characteristic polynomial. And the trace of the matrix is the negative of the coefficient of our linear term in our characteristic polynomial. So when we get that, when we understand that connection with the trace and the determinant and its characteristic polynomial, whenever we have a 2 by 2 matrix, we don't have to apply this this step anymore. We can just go straight into the characteristic polynomial. Okay, so any questions about that? That's problem number 17. Now let's look at homework number 5. Number 8. Okay, so this is going back to linear transformations. Okay, this is T1. This goes from R2 to R2. And they're telling you what the linear transformation is. It's 2x plus 7y, 8x plus 29y. And they're saying find the inverse. So they're asking you, what is the inverse transformation? Okay, so remember, for linear transformations, for any linear transformation, it can be represented by a matrix. So first we have to find the standard matrix representation of T1. So what is the matrix representation of T1? How do we do that? Does anyone remember how we do that? Several ways we can think of this. So T1, sometimes writing it this way might be a bit easier to see. So T1 takes a column vector x1, right? Right. Well, Mir, be careful. I don't know how you're treating the 2a. Are you treating the 2a as a row or as a column? As a row. Yeah, be careful with that. It's not quite a row. 2a is not a row. Because if you look at it, right? If you look at it, you can think of it this way: 2x 2x plus 7y, that's the first coordinate, and then you got 8x plus 29y. If you were to separate this, this can be written as 2x 8x plus 7y 29y, and then you can take out the x, and this becomes 2 8 plus 7 29y. But then you could treat this is a linear combination, right, of the columns. So this you could treat this as 2 8 7 29 xy. So the matrix will be 2 8 as a column and 7 29 as another column. The more standard way, of getting that is when you find what the standard basis gets mapped to. What are the elements in the range when your input is a standard basis? So remember the standard basis for R2 is E1 and E2, right? So what happens when I plug in T of E1? Well, according to the problem here, I get 2 times 1 plus 7 times 0. Why? Because remember what E1 is. E1 is 1 comma 0. And then comma, and this becomes 8 times 1 plus 29 times 0. So I get 2 comma 8. So that's 2 comma 8. That's the first column. Remember, TE1 gives you the first column of A, of its matrix representation. TE2 gives you the second column. So this would be 2 times 0 plus 7 times 1, comma 8 times 0 plus 29 times 1. And I get 7 comma 29. So what is A? A is the matrix representation of T1. So this is 2 comma 2 8, first column, second column is 729. Now that's if I go from if I go using T1, I plug in X comma Y, and then I apply this transformation and I get a new transformation. Okay. Now, how do we find the inverse? So remember what T1 is. T1 takes a vector X comma Y. You put it at T1, right? T1 is a transformation, right? And what gets spit out is T1 of XY, whatever that is. This is the input. This is the output. Now, what does T1 inverse do? T1 inverse takes the opposite direction, right? It takes some output, which is the output of the T1 is the input of T1 inverse, and the output is the result of that, right? So if I call this X comma Y, then I get some output T1 of X comma Y. So in order to find what that inverse is, how do you think that's connected, or how do you think finding the inverse linear transformation is related to the original linear transformation? How are they related with respect to their matrix representation? So if the matrix A characterizes T1, what do you think is going to characterize T1 inverse? A inverse, that's right. That's right, guys. A inverse is the linear transformation, the inverse of the linear transformation that's represented by A. So all I really need to do is find A inverse. So I know what A is. What is A inverse? Remember what A inverse was? It's 1 over AD minus BC. And then what is this? This is DA. And then you subtract negative B, negative C. So what's going to be A inverse? Well, what's the determinant of this? 2 times 29 is 58. Subtract it from 56, so it's 2. So A inverse is 1/2. And then you switch the diagonal entries, which is 29 and 2. And you negate the 7 and the 8. Got it? Now that's T inverse. So T inverse, when you plug in X and Y, what happens to it? You apply A inverse to X and Y. So A inverse is what? Let me just put the half inside. So I get 29 over 2 minus 7/2 minus 4 positive 1. So then I am applying 29 over 2, negative 7/2, negative 4, 1. And then when I apply the matrix multiplication, I get 29 over 2x minus 7 over 2y, negative 4x plus y. And then if you want to put it as a comma, right? As a comma delimited form, you would write it as 29 over 2x minus 7/2 y, comma, negative 4x plus y. And this would be T inverse. Is that clear? Does everyone understand how to find that linear transformation? The inverse? So then once we have this, once we have part A, this is part A. All of this is only part A. We're going to skip part B briefly because part C follows from part A. So part C asks, using part A, it is given that T1 of x comma y is 5 comma negative 4. And then this is from part A. This T1 is from part A. The question that asks, find x and y. So how do you find x and y? How would you find x and y given what we found in part A? Plug it in. What do you mean by plug it in? Plug it into what? Plug what into what? Exactly. For x and y. Okay. So we're going to plug in 5 comma negative 4 into the inverse of t. Why am I applying the inverse? Because the inverse is exactly what the opposite of what T1 is doing. T1 takes something, x comma y, and gives me 5 negative 4. The inverse gives me 5 negative 4 as the input, and the output is exactly what x comma y should be. A minus 1 minus b. Oh, A inverse. Yeah, you could, I think you can think of it that way, right? You can think of it as T1 xy is equal to A xy equals b, right? Which is 5 negative 4. You can think of it as this being my b, right? And then what's xy? Well, it's A inverse b. So you can think of it that way. Exactly right. So I'm applying the inverse, or I'm just applying the rule, which is given by the inverse, right? If I think of it as a matrix multiplication, the result of this is this. Do you see? So it's like it's synonymous. It's the same. I'm just going to plug it in. So according to the formula, this becomes 29 over 2 multiplied by 5 minus 7 halves multiplied by -4, comma -4 times 5 plus -4. And it's going to be some decimal for the first coordinate. The second coordinate is -20 minus 4, which is -24. And then you got 29, 29 times 5 divided by 2. 72.5. And then this will be a plus. The 2 goes into 4 twice, so you get plus 14. And so you get a total of 86.5. Okay. So that's going to be the coordinates for t inverse when you apply 5, -4 to it. So any questions about this part the part C? And now part B is the same idea as the same kind of problem as part A. The only difference is T2 is now R3. Taking something from R3 and mapping it to R3 as well. So we got T2 of x comma y, z. It's x plus z, x plus y, y plus z. And I want to find the inverse. So again, first I need to find the matrix representation of T2. So what is the matrix representation of T2? You can do this using the standard basis method, right? Plugging in E1, E2, and E3. Or you can try to visualize this as a column vector, x plus z, x plus y, and y plus z, separating it according to the variables. So this becomes x, and then 1, 1, 0. This becomes y. So let me just write this over here. So this becomes x plus z, x plus y, y plus z. And this can be written as x 1, 1, 0 plus y 0, 1, 1 plus z 1, 0, 1. But this is really the matrix 1, 1, 0, 0, 1, 1, 1, 0, 1 multiplied by the column vector x, y, z. It's the same thing. So this matrix here represents T2. So I'm going to call this A 1, 0, 1, 1, 1, 0, 0, 1, 1. Right? And now I want to know T inverse of x, y, z. I'll call this 2. So it's T2 inverse. To find that out, I need to figure out what A inverse is, because this is the same thing as saying A inverse of x, y, z. So what is A inverse? Well, for this one, I think using your calculator will be the best bet. Do this quickly. Second, second matrix. Want the 3 by 3, so I get 1, 0, 1, 1, 1, 0, 0, 1, 1. Then I do A inverse. And I get 1/2, 1/2, negative a half, negative a half, 1/2, 1/2, 1/2, negative a half, 1/2. So now that I have the inverse, I want to know what T2 inverse looks like when I plug in X, Y, Z. Well, this is the same thing as saying A inverse of X, Y, Z. And then it looks like 1/2, 1/2, negative 1/2, negative 1/2, 1/2, 1/2, 1/2, negative a half, 1/2. Column vector X, Y, Z. So this will look like X over 2 plus Y over 2 minus Z over 2 negative X over 2 plus Y over 2 plus Z over 2 X over 2 minus Y over 2 plus Z over 2. Or you can write this as a comma delimited form. This is X over 2 plus Y over 2 comma negative Z, pardon me, not comma, negative Z over 2 comma negative X over 2 plus Y over 2 plus Z over 2 comma X over 2 minus Y over 2 plus Z over 2. Okay, any questions about finding linear transformations, matrix representations of them, or finding the inverse matrix representation of linear transformations? And then part D asks, find given for part D that T2 of X, Y, Z is 5, negative 3, negative 1, find X, Y, Z. Well, that's the same thing again, right? It's like saying T2 inverse of 5, negative 3, negative 1, and you're plugging that in. You're plugging that in. So this becomes 5 halves minus 3 halves plus 1/2, comma, negative 5 halves minus 3 halves minus 1/2, comma, 5 halves plus 3 halves minus 1/2. 5 minus 3 is 2. 2 plus 1 is 3 halves. This is negative 9 halves. And you get 7 halves. So for our X is 3 halves. Our Y is negative 9 halves. And then our Z is 7 halves. Does this make sense, guys? Make sense? Clear? Any questions about linear transformations? That's a good question to go over. Very good with how matrix representations are related to linear transformations. Okay, next. What else do you guys got? So we've done linear transformations. We did a little bit of characteristic polynomial with eigenvalues. So where else should we go with this? No problem, Saida. Homework number 9. So Sam, and for everyone else, there will be a review sheet, but the review sheet will only cover everything after exam number 2. So it's going to be a lot shorter than the other ones, and it'll be posted later this week, so you guys can go over that. For now, we're just going over the homework problems, and everything that is covered on exam number 2 and exam number 1 will be also covered in the final, and you can use the review sheets that already were given for those exams. So I'm not giving new review sheets for old material. I'm just giving a new review sheet for the newer material after exam number 2. Okay. So homework number 9, problem 13. So let's go look at Baldwin. Number 13. Yeah, so let's look at that. So this is homework number 9. Number 13. So it says W is a subspace, right? Where every vector looks like this. R minus 5s plus 4t, 3r plus 3s minus 2t, 3r plus 5s minus t, 4r minus 3s plus 2t. Every vector in W looks like this. It says, find a matrix W, find a matrix A such that W equals the column, equals a column space of A. So we want to find A so that the column space of A is W. It sounds like you're doing more than you should be, right? It sounds like you're doing like a lot of stuff here, but really you're just rewriting this. A lot of this stuff is just rewriting. When I rewrite this, I can rewrite this as the following. You see, 1, 3, 3, 4 plus S, negative 5, 3, 5, negative 3 plus T, 4, negative 2, negative 1, 2. Do you agree? Right. But this is actually a linear combination of columns or column vectors. So I can create a matrix that looks like this. Do you see that? So W is really the column space of A. This is it. It's the column space because when I multiply this, what am I doing here? This is the column space of A. Column space of A is the linear combination of the columns. So I created a matrix where the columns are indeed these columns. So this is my matrix. I'm done. The column space of this matrix is W. And again, the column space is the linear combination of the columns of the matrix. So make the matrix with these columns. And by doing so, the column space of this matrix is what W represents, which is a linear combination of the columns. It's kind of like saying the same thing again and again. Okay. That's why your A matrix is a 4x3 matrix. You have 4 rows and 3 columns because you have 4 components, but you only have 3 variables. So does that make sense? Yeah. Again, a lot of this stuff is just rewriting. Okay, so we get another one. Homework number 9. Problem set. Problem number 17. Oh, nice one. So homework number 9, number 17. So it says A, right? A is a matrix, -9, -6, -3, 6, 3, 2, 1, -2. And it says find the basis for the null space. This is a very typical problem. Basis for null space of A. What's the null space? So remember, the null space is related to the solutions to the homogeneous system. So I'm asking, hey, what's the basis of elements that represents the X here? Then when I multiply it by A, it gives me 0. Because this is a 2x5 matrix, it's not a square matrix, right? We can't find the inverse of this. It doesn't make sense to do so. It doesn't have an inverse as the traditional way of what inverses are in square matrices. So the most straightforward way of doing this is using the row reduced echelon form, finding the row reduced echelon form of A. So then that requires me to plug it in the calculator and find the inverse. I find a row reduced echelon form. So I am going to enter my matrix. This will be 2x5 this time. And so the first entry is -9. And I got -6, -3, 6. Oh, whoops, it should be 2x4. Pardon me. It should be a 4, not a 5. -3, and then we got 6. We got 3. We got 2. We got 1. -2. Then quit. We go back to matrix. We first do the row reduced echelon form. So second matrix, go to math. And we go to row reduced echelon form, and I want to get the row reduced echelon form of the matrix A. And when I do so, I want to make sure I can see what's happening here. So I got this matrix here. So I got 1, first row, 2/3, 1/3, -2/3, and then I got 0, 0, 0, 0. Okay, so now the question is, how do we interpret the row reduced echelon form? Right, that's the question now. What does this even mean now? Remember, we have 4 columns, and these 4 columns relate to the four variables that we have. And so we can create an equation. The first row, we only have one row to worry about. The other row we don't worry about. We only have one pivot. So then what we have here is the equation x1 plus 2/3 x2 plus 1/3 x3 minus 2/3 x4 equals 0, which means that x1 equals negative 2/3 x2 plus 1/3 x3, sorry, minus, plus 2/3 x4. Do you see? This is a what? This is a pivot variable. But what are these? These are free. There's nothing else. They're not bound by anything. They're free. So if I want to write this now, if I want to write the solution, x, which is x1, x2, x3, and x4, x1 will be negative 2/3 x2 minus 1/3 x3 plus 2/3 x4. This will be x2, x3, and x4. This will be my vector, right? This is what my vectors will look like in the null space of this matrix A. But this looks kind of weird to express this way. So I'm going to separate this in terms of x2, x3, x4. So x2, the column vector will be negative 2/3, 1, 0, 0. Plus x3, the column vector would be negative 1/3, 0, 1, 0. Plus x4 will be what? 2/3, 0, 0, 1. This is the null space, guys. This is the null space of A. You have to know what you're finding. So the null space is a linear combination of these three linearly independent vectors. They're linearly independent. Because they're linearly independent and they span, because of the linear combination, the null space of A, they're the basis. So what's the basis? Basis for the null space of A. It's the vectors negative 2/3, 1, 0, 0, comma, negative 1/3, 0, 1, 0, comma, 2/3, 0, 0, 1. And of course, any multiple of these, any scalar multiple of these three vectors will still be a basis vector, a basis for a null space. So the basis is not a unique set. Is this clear? You have to know how to do this, especially on the exam, especially exam number 2. We had a lot of questions like this, similar. You have to know how to interpret the null space and how do you get that information from the row reduced echelon form. Okay, does there any questions about this problem? Is that clear now? Does everybody understand how to find the basis vectors of a null space of a matrix given the row reduced echelon form? It comes directly from the row reduced echelon form. We rewrite it a bit and then we see, oh, these are the vectors. Okay. All right, so that's problem number 17. And then we're still in homework number 9. Looks like homework number 9 had some difficulty. And we're gonna do number 3. Yeah. Okay, so this is homework number 9. Number 3. So we have 2 ordered bases. We have one basis that looks like the following: -1, -1, 1, -1, -2, 1, -1, 1, 0. Then we got C. -2, -1, 1, -2, -2, 1, -1, 1, 0. And the order matters. So we want to find the change of basis matrix from B to C. So I want to find the matrix. So transition matrix from B to C. So remember how we do this? How do we do this? What's the procedure? Remember, what do we put on the left side here? And what do we put on the right? In this case, what's our old and what's our new? C's are old, or C is our new basis and B is our old. We put the new first and then the old, right? So we're going to put them as columns. So the new is going to be -2, -1, 1, -2, -2, 1, -1, 1, 0. And then B will be -1, -1, 1, -1, -2, 1, -1, 1, 0. And then mirrors right. We do the row reduced echelon form. The idea is that on the left side, you should get the identity. And on the right side, you will get the transition matrix from B to C. Let's do that. This will be a 3x6 matrix. So second matrix, and then we edit 3x6. -2, -2, -1. A lot of negative ones. -1, 1, 1. Another -1. -2, 1, -1, -2, 1, 1, 1, 0, 1, 1. Okay. Then we do row reduced echelon form of that. And then we got 8. And so then our matrix is -2, 2, 1, 1, 0, -1, 4, -3, -1. Let me just make sure I got the right. B to C. Oh, I think my calculator has officially stopped working as an emulator here. I can't show it to you guys again for some reason. Stopped. So make sure you put the matrices correctly here. -2, -2, -1. So the first row should be -2, -2, -1, -1, -1. B to C. Yeah, okay, so this is the correct. All right, I don't know what happened with this emulator here, so I'll stop sharing that. So when you put that in your calculator, the result of the row reduced echelon form is on the left, you get the identity, and on the right, you get 2, -1, -1, 1, 0, -1, 0, 0, 1. And this is my transition matrix. That's the transition matrix. So I'm going to write it again. So the transition matrix from B to C is 2, 1, 0, -1, 0, 0, -1, -1, 1. Okay. Now part B asks for the transition matrix in the opposite order. If I want to go from if I want to go from C to B. But remember, these transition matrices should be inverses of one another, right? So if I go from B to C and then from C to B, I should go back to the original. So they should be inverses of one another. These are inverses. If they're inverses, that's pretty nice because then to go from the transition matrix from C to B, it's the same thing as saying the transition matrix from B to C, but take the inverse of it. So take the inverse of the upper matrix. So put that matrix as a 3 by 3 matrix. You get 2, 1, 0, -1, 0, 0, -1, -1, 1. Take that matrix and take the inverse of that. And what you get is 0, -1, 0, 1, 2, 0, 1, 1, 1. And that's all. So the key to this problem is understanding the procedure from going from one basis to another. And that entails creating a augmented matrix where the left side of the matrix are columns of the new basis that you're going into, and on the right are columns of the old basis vectors. You perform a reduced echelon form, and then the matrix that appears on the right, which on the left should be an identity matrix, but on the right, it should be the transition matrix for the desired transition matrix from one basis to the other basis. Okay. So that's that. And then the next one is homework number 4, problem number 8. Okay, if you have questions, please let me know. Even of the ones that I go over. Homework number 4. All this stuff should be crystal clear when you come to the final. Crystal clear. So homework number 4, number 8. Okay. Okay, number 8. So A is a 2 by 2 matrix for -3, 1, -1. And B is a 3 by 3 matrix, -1, -2, -3, -3, -2, -3, 3, 5, 2. Okay. And then it says part A. It says find the elementary matrix E1 that multiplies the first row by, they're telling you exactly what to find. So E1 is the elementary matrix that multiplies the first row of A by a fourth. So what is that going to look like? And A is a 2 by 2 matrix. So E1 will be 2 by 2 matrix. So what will E1 be if you're only multiplying the first row by a fourth? Remember, elementary matrices are just the identity matrix, and you're applying the row operation on the identity matrix. So what would E1 look like? Anybody? We did this for which one would do this for? We did this for like the diagonalization of matrices recently, right? No, for the LU factorization, pardon me. When we did the LU factorization, we talked about elementary matrices again. So this should be quick. This should be easy. It's from the beginning of the semester. Right. This should be a fourth, guys. This one here should be a fourth. This multiplies, if I multiply A by E1, if I do this, E1 multiplied by A, then, and when I multiply it by A, this matrix by this elementary matrix, it's going to multiply the first row by a fourth. And then once we know this, we should also know immediately the inverse. Well, if it multiplies, what's the inverse of multiplying by a fourth? What would be the inverse? Right. If you multiply something by a fourth, then the inverse will be multiplying by the reciprocal of a fourth, which is 4. So this should be 4. The first entry should be 4. 0, 0, 1. Done. That's E1. Quick. Now E2, what does E2 say? E2 says find a matrix the elementary matrix that multiplies the second row of A by -5. So this starts to become kind of straightforward, right? The second row. So if it's the second row by 5, what would that -5 would look like? -1, -5, 0, 0, right? And then what's the inverse? Multiply by -5 to find the inverse of that. I need to multiply by -1/5. So this is 0 and -1/5. Sorry, it should be 1. So jamming, we haven't done question number 14 yet. But we can do that after we do this one and after, did we do 14? No, we didn't, right? We did 13. Yeah, we didn't do that one yet. Okay. So that's E1, that's E2, and E2 inverse. We got that one. We got this one. We got this one. We got this one. The next one. What does the next one say? E3. E3 says what? It switches the first and second rows. So then what is the invert? What is the E3 then? What does E3 look like if you switch the first and second rows? Right, it's going to look like a 0, 1, 1, 0. It's like taking the identity matrix and just switching the rows. That's exactly what it is. Now, what's the inverse of this? What's the inverse? The inverse is the identity? Think about it, right? I want to switch row 1 with row 2. The inverse, whatever that means, has to result in the original state. So if I took a matrix in original state, I switched it from 1 to 2, 2 to 1, and I want to reverse it to the original state, what do I have to do? Oh, it's in exactly. I just apply the matrix again. So this is a special matrix where the inverse is itself. So the inverse here is 0, 1, 1, 0. And you can check it for yourself. You can check it that when I apply this matrix to this matrix, I get the identity. That's always a way to check whether a matrix and another matrix are inverses, is if when you multiply them together, you get identity. Okay? See, a lot of this is just review. E4. So now this one is the adding 4 times the first row to the second row. This is probably the hardest one of the different kinds of elementary matrices. There's ones that just swap the rows. That's the easy one. There's ones that just multiply one row by a particular scalar, which is also a simple one because it's just replacing the diagonal entry with that scalar multiple. And then the hardest one here is when you have to multiply a scalar multiple of one row to another one. So here I'm adding 4 times the second row. 4 times the first row to the second row. So what I'm doing is I want to find what matrix takes the first row and multiplies it by 4 and adds it to the second row and makes that the new second row. How would I represent that as a elementary matrix? So the mirror says 1, 0, right? Because the first row stays untouched. So the first row, we keep it. And then the second row, we're taking the first row and we're adding it to the first. We're adding the 4 times the first row to the second row. And this should be correct. So then what would be the inverse? What would be the inverse? You can find the inverse many ways, right? You can actually just do the 2 by 2 thing. And then you see what happens. So you're saying 1, 0, 1/4 1, right? Now let's try that. 1, 0, 4, 1, and then let's multiply that by 1, 1/4, 0, 1. I should get the identity when I do that. And when I do that, I get 1, right? And I get 0. And what happens here, though? What happens here? I get 4 times 1 plus 1/4. I get 4 plus a fourth. And then I do 4 times 1 and I get 1. I don't get the identity. So this is not, even though it may feel right, right? It may feel the intuitive way would be, oh, if this is a 4, then this should be a fourth. But that doesn't cancel it out. I want this to be canceled out here, to be 0. And if you study 2 by 2 matrices and you find the inverse, how do you find the inverse of 2 by 2 matrix? Find the determinant, which is just 1 in this case. You switch these entries, but they're the same, so just keep it, and then you just put the negative. This should be -4, not a fourth. And so then if you want to try that out now, 1, 4, 0, 1, and you multiply that by 1, -4, 0, 1, you get 1, 0 in the first row, right? And then in the second row, Look what happened. 4 times 1 plus 1 times negative 4 is 0. And then you get 1. So this is indeed the correct inverse. Okay, make sure you guys see the difference. See why this is indeed the inverse and not the previous suggestion. Okay, so hopefully we can speed this up now. And the fifth one, we want a 3x3 matrix, E5. So we want a 3x3 matrix that multiplies the second row by a third. So we want a third the second row. So how do we do that? Well, we just want to multiply the second row by a third. So only the diagonal entry here will be a third. Everything else will be ones on the diagonal, and everything that's not on the diagonal will be zeros. That's a quick one. So then what's E5 inverse? It's going to be the inverse of 1/3, which is 3. Okay, so that's that. All right, next we have E6. E6 is a multiplies the third row, 3x3 again. This multiplies the third row by -4. So take third row and multiply by -4 to the third row. And so this becomes 1, 1, -4, 0, 0, 0, 0, 0, 0. Okay, and then the inverse is 1, 1, -1/4, 0, 0, 0, 0, 0, 0. Next, you want to switch the first and third rows. So R3, I want to swap it with R1. So what does that look like for a 3x3 matrix? If I want to swap row 3 with row 1, what does that mean for the elementary matrix? What would the matrix look like when you swap rows 1 and 3 in a 3x3 matrix? Remember that elementary matrices are just the identity matrix, but that is the row operations are being applied to the identity matrix. So if the identity matrix for 3x3 is 1, 0, 0, 0, 1, 0, and 0, 0, 1, and I want to swap row 3 and 1, that's exactly what I'm going to do. I'm going to swap these rows here. And so then I get 0, 0, 1. The second row stays intact. This becomes 1, 0, 0. Then the identity, what's the inverse? What would be the inverse of E7? If I swap rows 1 and 3, I want to get to the original row, the original matrix, or I want to apply the opposite of swapping rows 3 and 1. So what's going to be the identity? What's going to be the inverse matrix? Anybody out there, guys? Anyone? Are you guys following what I'm doing? Does this make sense? Am I just speaking to myself? What is it? No, nobody knows the inverse. Oh, thank you, Baldwin. It does make sense. Great. So then what would be the inverse of an elementary matrix that switches rows 1 and 3 together, swaps it? We're almost done with the question. We just need to do these last two. Again, this is kind of like the same thing we discussed for the matrix that swaps rows 1 and 2 for the 2 by 2 matrix. The inverse, why I keep saying identity, the inverse of this matrix was itself, because if I swap these two rows together, then I would get the identity. So if I swap rows 1 and 2 and I swap rows 1 and 2 again, I get the identity matrix. So that's why for this one, it's going to be the exact same thing. If I swap rows 1 and 3 together and then I do it one more time, I get the identity, which means that the inverse is itself. So 0, 0, 1, 0, 1, 0, 1, 0, 0. Okay, and now the last one. The last one is multiply or add 4 times row 1 to row 3 into row 3. So this is E8. This is a 3 by 3 matrix that takes the first row, multiplies it by 4, and adds it to the third row and makes that the new third row. So what is my matrix going to look like? Remember, I'm taking the first row, multiplying it by 4, and adding it to the third row. Anybody can give us a clue? Anybody have an idea? Come on, guys. Where you guys at? This is elementary matrices. They're called elementary. Taking the first row of a matrix, multiplying it by 4, and adding that to the third row of the same matrix, and then making that new row. So how would we do that? Really, the question becomes, where do we put the 4? Where do we place the 4 in the identity? So this will all be the identity. 1, 1, 1. Now the question is, where do we place the 4? And that's it. And everything else will be zeros. So where would the 4 go? Row 3, first column. Very good. That's right. This will be 4. This is 0. This is 0. This is 0. This is 0. And that's 0. If I were to perform a matrix multiplication on the left by this matrix, then I'm going to add the first row a multiple of 4 of the first row to the third row and make that the new third row. Great. Thank you, Saida. So then now when we take the inverse, what would be the inverse? What would be the inverse? Think about the LU factorization. Think about what we just did here. When we had to do the when we had to multiply the first row by 4 and add to the second row, right? We put the 4 here, but then to find the inverse, we put the -4 in the same spot. So what do you think is going to happen with the 3 by 3? Same thing, guys. Same exact thing. It would be 1, 0, 0, 0, 1, 0, -4, 0, 1. Wait, actually, the last one is not this. The last one says add, I read it wrong. Add 4 times the third row to the second row. Yeah, I got that wrong. So this is actually not it. So I have to redo this. And the same token, redo this. So now that we changed it, that's good though. We changed it. A new variety. So what if we want to multiply the third row to the second row? How would you do that? Where would the 4 go? The 4 wouldn't go here. The 4, if you put it here, you're taking the first row, multiplying by 4 and adding it to the third row. I want to take the third row, multiply it by 4 and add it to the second row. So then it would be what? Row 2, column 3. There we go. Yeah, that's right. The 4 would go right here and zeros would go everywhere else. Yeah, the 4 will be in the second row, third column. So that means that when you multiply this row here, you're taking the second row and then you're taking the a scalar multiple of 4 of the third row and you're adding it to the second row. And so obviously, because now that 4 is there, you know that you have to just put the negative for the inverse in the same entry. So that when you multiply these matrices, those 4s and -4 will cancel out in the matrix multiplication. Okay, guys, so please review your elementary matrices. It's really not too much. The hardest part are these situations where you have a scalar multiple of another row being added to another row. But besides that, this should be straightforward. You definitely need to know elementary matrices for LU factorization. So yeah, so I'm gonna go in order. Someone asked before then, Interpret asked homework number 6, problem number 18. And then we'll go from there. So homework number 6, problem number 18. So Interpret thing. Homework number 6, problem number 18. Okay, very good. So this is a projection problem. Also very important to know how to do. So here we have P, we have A, and we got B. And then we have this line here. This is D, This is a perpendicular. And then we have these arrows here, right? Okay, and then it says AB, the distance P1. So say P1 is this. P1 is -1, 1. A is 3, 1. And B is 4, 2. And the question is, the distance from P to the line through the point AB. So they want to find this. What is D? So remember, this is not too bad of a problem, but it's not that straightforward. It's not that just like 1, 2 step. There's several steps here. What you want to figure out first is what's the projection. So let me just write this in neon. This here, this little segment here, this is the projection of the line AP onto the line AB, or the vector AB. So this segment here is the projection of this vector along this vector. If I can find this out, I'm not sure. Sorry, Siri just woke up. Okay, so if I find this projection, I know that if I subtract this vector with this vector, I would get the perpendicular vector. And this perpendicular vector, when you add this vector with this vector, gives me this vector, right? By the way we add vectors. And the length of this vector is the distance that we're considering. So the first order of business is to find the projection of AP along AB. So the first thing I'm going to do is I'm going to find what AP is. And I'm going to find what AB is. And how do you find AP? Do you guys remember this? How do you find AP? AP is the vector from A to P. How do you find that vector AP? P minus A, that's right. So it's like point P minus point A. So that's going to be what? -1 minus 3, 1 minus 1. And so I get -2, 0. So that's AP. And then what's AB? B is B minus A. So B is 4, subtract that from 3. And then it will be 2, subtract that from 1. And I got 1, 1. And then what's the projection matrix? I mean, what's the projection formula? If I call this AP, if I call AP, I'm gonna call this V, okay? So call this V. And then call this A, little a. So then if I want to rewrite this, this is the projection of V along A. What would be the formula for this? This is more of a formula question. It's V times A. Yeah, that's right. It's V times A, or V dot A, over A dot A, which is A norm squared. Multiply, you're missing one thing though, multiplied by A. You guys, don't forget that. This here, this here is just a scalar, because dot product gives you numbers. Number divided by numbers, and numbers is scalar. And you're taking this is the scalar associated with this vector A that gives you exactly the projection of the original vector V onto A. So what's V dot A? So V dot A is negative 2, 0, multiply dot product with 1, 1, which is negative 2. So the top here will be negative 2. And then what's a dot a? Well, that's just 1 squared plus 1 squared, which is 1 times a. And of course, these, yeah, it's not geometrically according to where it should be. But anyways, so this is negative 2 times a, 1, 1. So this should be negative 2 comma negative 2. That's the projection, right? So remember, the original vector v, this is v here, v is equal to the projection of v along a, and you add that, the sum here, I'm going to call this vector w, plus w, and w is in the orthogonal complement. That's another more fancy way of saying it's just orthogonal to that line. I know what this is. I know what this is. I can find what this is by subtracting, right? This missing vector w is v minus the projection. Oh, it's starting to look a lot like the Gram-Schmidt process a little bit. So what is v again? V again is negative 2, 0. What is the projection that I just found? Negative 2, negative 2. So negative 2 minus negative 2 is negative 2 plus 2, which is 0. And then 0 minus negative 2 is positive 2. So w is 2. W is 0, comma 2. So this vector here is 0, comma 2. And let me just see if the numbers here match up. 3, 1, 4, 2. Let's see, v dot a. Oh, pardon me. I added this incorrectly. A dot a is 1, 1, dot product 1, 1. And that's 1 times 1 plus 1 times 1, which is 2. Guys, this is 2. So this should be negative 1. So this should be negative 1. Is that going to change things? Yeah, it will. Because now the projection is not negative 2, negative 2. It's negative 1, negative 1. And when I subtract this, negative 2 minus negative 1 is negative 2 plus 1, which is negative 1. And then this becomes positive 1. And then that's w. This is w. Negative 1, 1. But what's the norm of, so the distance is the norm of w. What's the norm of w? It's the square root of negative 1 squared plus 1 squared, which is rad 2. And let me just see AP. Oh my goodness, guys. Oh boy. So another little mistake. Guys, don't make sure you check your work. Negative 1 minus 3 is not negative 2. As much as I wanted it to be, it's not. It's negative 4. So it's negative 4 comma 0, AP, right? That's V. So it should be negative 4 comma 0. So this should be negative 4. This should be negative 4. This should be negative 2. So this is negative 2 comma negative 2. The problem is this should be not negative 2, but negative 4. That's the problem. This should be negative 4. And then this here should be negative 2, negative 2. So this W will be negative 2, positive 2. So this should be negative 2, positive 2. So this should be negative 2, and this should be positive 2. So this should be rad 8. And rad 8 is approximately 2.8. 2.828 for dot, dot, dot. So please be mindful of the pluses and minuses when you add them, subtract numbers. And that's usually what's going to trip you up. It's the little arithmetic that you have to do. The more conceptual stuff is knowing why you perform what you did, like knowing why you need to even do the a minus p minus a and the b minus a. So you get these vectors, you get these vectors here. Oh no, you get this vector here and this vector here. And then you've performed a projection of this vector onto this vector to find this green vector here, the projection. Because now that I found the projection of v, I can subtract v with the projection of itself onto this line, so that when you subtract these two vectors, you get the orthogonal vector, and that orthogonal vector is the vector with which you want to find a norm of. And once you find that vector w, you can find a norm of it, and the norm of that vector is the length of the vector, which is the distance that point P is from the line AB. Okay, any questions about the procedure, outline procedure here? Are we good, Interpret? Good? So then the next one is homework number 10, problem 18. Homework number 10, problem 18. Yeah, we'll see. I may not have enough time to go over every single one. I will have office hours if you guys need extra time to go over this. So this is homework number 10, number 18. So again, this is one of those questions. 5, 12, negative 6, 4, 7, negative 4, 12, 24, negative 13. Last three of all, homework number 10 is all pretty tricky. Yeah. Well, this is the last one of the last three of homework number 10. I don't know if it's tricky, because it's finding the diagonalization of a matrix A. So it's pretty straightforward for finding them. What might be tricky is the matrix they give you. So that might be a problem. So the procedure itself is straightforward. You have to find the eigenvalues, and then the eigenvalues find the eigenvectors. And the eigenvectors are the columns of P, and the diagonals are the eigenvalues of A. But A here, the one that I see here, looks a little crazy. It does, actually. Yeah, so it looks like this problem requires you to have everything correct in order to get full answer. So maybe something went wrong. Okay, so how do you find the eigenvalues? You do the characteristic polynomial, right? So you do 5 minus lambda, 7 minus lambda, and negative 13 minus lambda. 24, 12, 4, 12, -6, -4. And then you take the determinant of this and equal to 0. So this requires a lot of computation. It does. And you can choose any row for this, or any column for that matter, and it'll be about the same amount. So let me actually expedite the process a bit. I'm gonna show you the power of Maple. Let's see. Can we use our calculators to get the eigenvalues on the exam? I don't think your calculator has that functionality, unfortunately, because it doesn't know how to, it's not a computer algebra system, so it doesn't know how to do this. If you were to plug in a matrix, a 3 by 3 matrix, and find a determinant of a 3 by 3 matrix, and the entries are variables, it doesn't know how to do that. It just knows how to compute matrix determinants of matrices, for example, that have explicit numerical values to it. So it knows how to do determinants upon numerical computation. But when you talk about algebraic computation, I don't think your TI-84 has that capability. It may have, which I'm unaware of, but I don't think it does. That's why sometimes you need a little bit more help with that. But if you are going to have to do this, I'm not going to give you a matrix this crazy. It's going to be something that, it might have zeros in them. So then you might have to apply the cofactor expansion upon the row or the column that has more zeros in it. So then it simplifies your computation. I'm not going to give you one like this, particularly on an exam. So you don't have to worry about that so much. But with Maple, and all of you are able to use, I don't know if you guys know, you guys can download Maple for free. Being students at CUNY. All right. So with the Maple, no, you shouldn't pay for it. If you go to the CUNY e-mall, if you go to the CUNY e-mall, you can download other things as well. I think you can download was it the McAfee, um, like the protection or virus protection or something like that. And you can also download what else can you download? I forget. There's another software package you can download, but one of them is Maple, and it should be free. Any regard, so when you have it, when you guys download it, you can actually use something called with linear algebra. So then you're downloading basically the linear algebra package, and then I'm gonna set the matrix to be so here they deal with rows. So the first row will be, let's see how to do this. Oh, okay, so I think I have to specify. Hold on. Yeah, you don't have to specify. So you can just write it out. So you can write this as 5 minus, they do have lambda, I think. Do they have lambda? They don't have lambda. Okay, so I'm going to treat it as x. 5 minus x. And then comma 4, comma 12. That's the first row. Then comma, second row. 12, comma 7 minus x, comma 24. They have Greek on the left. Oh, they do have Greek. That's right. So I can use lambda, but I wonder if they use lambda as a variable as well. I think they will. Let's do lambda. It doesn't really matter. You could do x. It's just lambda's just the convention. And then this is -6, -4, comma -13 minus lambda. And then you close it. And let's see. It should not, it should give me, hold on, maybe. Oh, that's right. So the cool thing about Maple is you're able to like correct whatever you did previously pretty quickly. So now we're talking. So now this is the rate. This is the matrix, right? So then now after you've downloaded the linear algebra package, you can actually use a function called determinant. You're taking the determinant of A. Boom. So this is my polynomial. And you can actually factor this polynomial. And you get exactly what you should get. So the polynomial here, the characteristic polynomial, is negative lambda minus 1, lambda plus 1 squared equals 0. So the lambdas are 1 and lambda equals -1. Maple is very helpful. Maple is a very powerful mathematical software package. Right? It's comparable to Mathematica. It's comparable. They do similar things. But I think symbolically speaking, Maple is probably a bit more superior than Mathematica with this symbolically. Computationally, I think maybe Mathematica is the better of, probably the best one out there. But yeah, you can also, you can solve these as well. You can solve the and this symbol here, the percentage symbol, is just the previous answer. If I set it equal to 0, and I can specify the variable that I want to solve for, and then I get exactly what lambda should be, which is 1, -1 twice. Okay, so those are my eigenvalues. And then I want to find the, let me see, can I do row reduced echelon form? I'm pretty sure I can. That would be very helpful. Oh, it does work. Okay, so you could do that. Okay, so then I'm gonna do but see, this is a little clunky though. You have to use you actually have to write out reduced row echelon form of, I'm gonna do A plus minus I. See what I is. Yeah, that doesn't, that's not, okay. What do you see? Identity matrix. Sorry, it should be identity matrix. So I have to actually specify identity matrix, and then this is 3 by 3. Oh, yeah, I see. Okay, yeah, it's not going to work this way the way I thought it would. But regardless, um, you find a row reduced echelon form of A minus, and this A is not the same. This A is this A. The A that I'm referring to, though, is the one, the original A that we had. Um, so you have to find the eigenvectors, and I think we're out of time. But I can continue this in office hours for those of you who are still able to do it. But after this, we find the eigenvalues. After finding the eigenvalues, we find the eigenvectors, which is probably, I think, where people mess up most on. But once you find the eigenvalues, you should be able to get the eigenvectors. And once you find the eigenvectors, you place those eigenvectors along columns. And that matrix with columns that are the eigenvectors of the matrix A, that's P. And so D here, D would be, the diagonal matrix would be 1, -1, -1. This would be the diagonal matrix. Again, the diagonal matrix is a diagonal matrix where the diagonal entries are the eigenvalues. And -1 repeats twice because it has an algebraic multiplicity of 2. Okay, so I'll continue with this